Welcome back to the machine learning course. In the previous video, we introduced regression and learned what it is, where it's used, and how it differs from classification. Today, we're moving one step further by learning the most fundamental regression algorithm, linear regression. We'll also briefly discuss multiple linear regression because it's simply an extension of the same concept. In this lecture, we'll understand the intuition, the mathematics behind the algorithm, the assumptions we need to satisfy, and then we'll implement everything in Python. So let's begin. Linear regression is one of the simplest and most widely used supervised learning algorithms. Its purpose is to predict a continuous numerical value by learning the relationship between the input features and the target variable. You can think of it as drawing the best possible straight line through the data points. Once this relationship is learned, the model can predict the output for new data that it has never seen before. The main objective is simple: find the line that minimizes the prediction error. Let's first understand simple linear regression. Here we use only one independent variable to predict one dependent variable. For example, predicting a person's salary based only on their years of experience. The equation is y equals b0 plus b1x. Here y is the value we want to predict, x is the input feature, b0 is called the intercept, and b1 is the slope, which tells us how much y changes when x increases by 1 unit. The graph shown here illustrates the best fit line that the algorithm learns from the data. Now suppose one feature isn't enough. If we're predicting house prices, the price depends not only on the size of the house, but also on the number of bedrooms, location, age of the house, and many other factors. This is where multiple linear regression comes in. Instead of using one feature, it uses two or more independent variables to predict a single output. The idea remains exactly the same. The only difference is that now multiple features contribute together to make a prediction. Let's briefly understand how linear regression finds the best fit line. First, the algorithm assumes a straight line relationship between the input and the output. Next, it calculates the difference between the actual value and the predicted value. This difference is called the residual, or error. Since some errors are positive and some are negative, we square them so they don't cancel each other out. Finally, the algorithm searches for the values of b0 and b1 that produce the smallest total error. This method is called ordinary least squares, and it gives us the best fit line for the data. Before using linear regression, we need to make sure that some important assumptions are reasonably satisfied. First is linearity, meaning the relationship between the features and the target should be approximately linear. Second is independence, where observations should not depend on each other. Third is homoscedasticity, which means the variance of the errors should remain roughly constant. Fourth is normality of errors, where the residuals should be approximately normally distributed. And finally, no multicollinearity, meaning the independent variables should not be highly correlated with one another. These assumptions help ensure that our model produces reliable and meaningful predictions. Now that we've understood the theory, let's move to the Python implementation. We'll build a linear regression model step by step and see how everything we've learned is applied in practice. Step 1. We begin by importing the required libraries. We'll use pandas for handling the dataset, NumPy for numerical operations, matplotlib for visualization, and Scikit-learn to build our linear regression model. Step 2. Next, we create the dataset and take a quick look at it to understand the available features and the target variable. It's always a good practice to inspect your data before building any model. Step 3. Next, we divide the dataset into training and testing sets. The training data is used to teach the model, while the testing data helps us evaluate how well the model performs on unseen data. Step 4. Now we create an instance of the linear regression model and train it using the training data. During this step, the algorithm automatically finds the best fit line by minimizing the prediction error. Step 5. Finally, we evaluate our model using regression metrics such as mean absolute error, mean squared error, root mean squared error, and the R-squared score. These metrics tell us how accurate our predictions are. Step 7. Lastly, we visualize the regression line along with the data points. This helps us clearly see how well the best fit line represents the relationship in the dataset. Let's quickly summarize today's lecture. We learned that linear regression predicts continuous values by fitting the best possible straight line through the data. We also saw the difference between simple and multiple linear regression. Then we understood how the algorithm minimizes prediction error using the ordinary least squares method and discussed the key assumptions that should be satisfied before applying the model. Finally, we implemented the complete workflow in Python, from loading the dataset to training, evaluating, and visualizing the model. In the next lecture, we'll move on to polynomial regression, where we'll learn how to model nonlinear relationships that a straight line cannot capture. If you found this lecture helpful, don't forget to like the video, subscribe to the channel, and turn on the notification bell so you don't miss the upcoming videos. Thanks for watching, and I'll see you in the next lecture.